Hello, all you cool cats and kittens. Today we are going to learn the unit circle. Basically, we're going to take our special triangles and we're going to insert them into this special circle that we call the unit circle. Circle has this equation x squared plus y squared equals 1, and if you remember from geometry, that tells us that it has a center that's at 0, 0 at the origin, and its radius is the square root of 1, which is 1. That's what makes it the unit circle, because its radius is exactly 1 unit. Around the unit circle, the values of sine of theta, any angle that we create in standard form around the unit circle, sine and cosine become the y-coordinate and y-coordinate. I'm going to show you why that's true in a moment. Of the point where the terminal side of that angle intersects or touches the unit circle. So in this diagram on the left side of the screen, we see that there is a triangle that's been inscribed into the unit circle. It's touching the edge of the unit circle at point P, and the distance to point P would be a horizontal distance of x, so the x-coordinate is there as x, and it would be this vertical distance of y, and we can see there the y-coordinate labeled. And here is the angle we've created. The initial side is the positive x-axis, and our terminal ray is here, creating the radius of the circle, and theta is here as our reference angle. So within this circle, if we look for sine of theta, and we look at our triangle, the sine of theta would be the opposite side, which is y, over the hypotenuse, which is 1, always 1 in the unit circle, and that simplifies to just y. When we look for cosine of theta, we look at the adjacent side, which is x. We put that over the hypotenuse of 1, and of course that just simplifies to x. So when we think about coordinates in the unit circle around the edge, those x and y coordinates can be represented by cosine of the angle and sine of the angle, where the terminal ray intersects the unit circle. And as we learn the unit circle, we're going to begin with our special triangles. We're going to inscribe those into the unit circle. So we want to do a little review from our standard 45, 45, 90 and standard 30, 60, 90 triangles about sine, cosine, and tangent values. Looking in our 45, 45, 90 triangle from either 45-degree angle, sine is opposite over hypotenuse, which would be 1 over the square root of 2. And when we rationalize that, we get the square root of 2 over 2. Cosine results in the same thing, square root of 2 over 2. And when we do tangent of 45, we do the opposite over the adjacent, which is 1 over 1, or 1. So wherever we see a 45-degree angle, we know those values. As we look at a 30-degree angle, sine is opposite over hypotenuse, or 1/2. When we look at cosine of 30, that is the adjacent side over the hypotenuse, root 3 over 2. And when we do tangent of 30, we are doing the opposite over the adjacent, which would be 1 over root 3. Then we would rationalize to get root 3 over 3. Sine of 60, opposite over hypotenuse, root 3 over 2. Cosine of 60, adjacent over hypotenuse, 1/2. And tangent of 60, opposite root 3 over adjacent 1, which simplifies to root 3. And of course, you've been working on memorizing those, so those will come easily as we fill in our unit circle on the next slide. Excuse me. So we're going to fill in all of the angular measurements around our unit circle in degrees and radians. And then we're going to fill in all of the coordinates around the unit circle as we rotate. And we are going to look for patterns. That is really important. So we're going to start with our 30-degree angle. I promise to go back to the others. But the first 30-degree angle we'll find is going to be right here. So let's write 30 degrees, and we can call this theta for the time being. We're going to convert theta of 30 degrees to radian measure by multiplying by pi over 180, and that would give us pi over 6. Here's the point where our terminal ray intersects the unit circle, and we're going to think about what would happen if we made a triangle here to come up with our x and y coordinates. Well, we remember that the x-coordinate is the cosine of that angle, and the y-coordinate is the sine of that angle. Since this is a 30-degree angle, the x-coordinate is whatever the cosine of 30 would be. The x-coordinate is this adjacent side over the hypotenuse in the unit circle, which we know is 1. That simplifies to x, and the cosine of 30 is the square root of 3 over 2. The y-coordinate, up and down, that's the opposite side. That's going to be the sine of 30, and we know that is 1/2. So we can get those coordinates by identifying the angle that we have made and knowing its cosine and sine values. So we learned earlier in the week about reference angles. We want to look for everywhere on the unit circle that there is a reference angle of 30 degrees. And here would be our next reference angle of 30 degrees right here. But that's not really how we measure that angle. We should measure it from the positive x-axis in the positive direction, rotating counterclockwise. That's 150 degrees. Now, when I think about radians, I try to make life as easy as possible. And if I know that 30 degrees is pi over 6 radians, and 30 goes into 155 times, then the radian measure must be 5 times pi over 6. They are multiples. So we have a 30-degree angle over here as well, 30-degree reference angle, which forms the same triangle that we were looking at. Oh, excuse me. I wrote 5 pi over 6 and 150 in the wrong spot. Well, sorry about that. So now that we have our 30-degree reference angle, we can see we've created exactly the same triangle that we did in the first quadrant. So our x and y values should generally be the same because we have a 30-degree reference angle. It's the same triangle. But we have to remember that we're in the second quadrant. And in the second quadrant, our x values are negative, but our y values are positive. So we would start by saying, okay, this is 30 degrees, so we know it's root 3 over 2 and 1/2 for cosine and sine. But because we are in the second quadrant, our x-coordinate is going to be negative, just like it would be in any other point in the second quadrant. Again, looking for our 30-degree reference angles, our next one is going to be in the third quadrant. Write this one in the right spot this time, which would be right here, a 30-degree reference angle. So that's 180 plus another 30 degrees, which would take us to 210. 210 divides by 30 7 times. So this would be 7 pi over 6 when it comes to radians. Now, because it's a 30-degree reference angle, I know that this is root 3 over 2 and this is 1/2. But we're in the third quadrant where both x and y coordinates are negative, so we're going to make both of those negative. And that is the x and y coordinates where the angle 210 intersects the unit circle. We're going to go into the fourth quadrant and look for our final 30-degree reference angle, which would be right here. That's 30 degrees shy of a full rotation, which would make this 330 degrees. 30 goes into 330 11 times. So 11 pi over 6 would be the radian measure. Because the reference angle is 30 degrees, this is root 3 over 2 and 1/2. But we're in the fourth quadrant. So the x-coordinate would be positive, but here the y value is negative. So the unit circle is a lot of repetition. Here are all our 30-degree reference angles. Here are the x and y coordinates at the point of intersection, which we could also label as the sine and cosine of each of these theta values. Our next special angle is 45 degrees. So 45 degrees would be right here. Sorry, I'm trying to change that color. You can identify all of these. 45 degrees right here. So let's write 45 degrees. And we would first convert that to radians by multiplying by pi over 180, and that would leave us with pi over 4. So we think back to our standard 45, 45, 90 triangle, and we ask what is the cosine of 45? And the answer to that question is root 2 over 2. So that is our x coordinate. The sine of 45, also the square root of 2 over 2. Where else can we find a 45-degree reference angle? We can find a 45-degree reference angle right here, which is 45 degrees shy of 180, which would make this 135 degrees. Converting that to radians, it is 3 pi over 4, because 45 goes into 135 3 times. And again, the x and y coordinates would be the cosine and sine of 45 degrees, because that's our reference angle, and that is the triangle we would make. So we're going to write down root 2 over 2 and root 2 over 2. And then we're going to think, wait, we are in the second quadrant. The x coordinate is negative. Our next 45-degree angle, reference angle, will be right here. That's 180 plus 45, which would take us to 225, which is the same as 5 pi over 4. It would create the same 45, 45, 90 triangle when we look at the reference angle. So root 2 over 2 for cosine, root 2 over 2 for sine. In the third quadrant, both are negative. Another 45-degree reference angle here. That is 45 degrees shy of 360, so that's 315 degrees, which is the same as 7 pi over 4. Again, cosine is root 2 over 2, sine is root 2 over 2, but we're in the fourth quadrant, sine is negative. On to our next special angle, which is going to be 60 degrees. We'll find the first one here, do this in green. So let's go ahead and put 60 degrees here. Converting that to radians would give us pi over 3. Now to find the point where it intersects with the unit circle, we need to remember what is the cosine of 60, and that is 1/2. And the sine of 60, which would be our y-coordinate, is root 3 over 2. We look for 60 again in the second quadrant. That would be right here. So that is 120 degrees, which would be 2 pi over 3. And again, cosine 1/2, sine root 3 over 2, but in the second quadrant, x is negative. Our next 60-degree reference angle here in the third quadrant, that's 180 plus 60, which would be 240 degrees. 240 degrees in radians is 4 pi over 3. You'll notice 60 goes into 244 times, so it's a multiple. Cosine 1/2, sine root 3 over 2, because it's a 60-degree reference angle, but in the third quadrant, both would be negative. And last but not least, our 60-degree reference angle in the fourth quadrant, right there. 360 minus 60 degrees would give us a 300-degree measure. Converting that into radians would give us 5 pi over 3. As with every 60-degree angle, the cosine is 1/2, and the sine is the square root of 3 over 2. But as we are in the fourth quadrant, a negative value for our y-coordinate. So we're doing pretty well, but there are still some blanks, and these are our quadrantal angles. So let's go to our first set here, which would be at 0 degrees, also at 360. 0 degrees is still 0 radians, and 360 degrees is a full rotation, which in radians is 2 pi. Now we can't really make a triangle, but we still want the x and y coordinates of where we intersect the unit circle. Remembering that we've created a radius right here, and the radius is 1. So when we think about the x coordinate of this point, we had to go out 1. We did not move up or down from the origin, so our y-coordinate is 0. Our next quadrantal angle would be the positive y-axis, which forms a 90-degree reference angle. In radians, that is pi over 2, a quarter of a full rotation. Now at 90 degrees, we can't make a triangle, but we can figure out our x and y coordinates, which would still represent cosine and sine. Our x-coordinate is 0, we did not move left or right, and our y-coordinate is 1. We went up all the way to the edge of the circle, 1 radius in the unit circle. On the left, 180, converting to radians, that's half of a rotation, or pi. Can't make a triangle, but we can calculate the x and y coordinates. We've gone all the way to the left, 1 radius of the unit circle, and since we went to the left, that is -1. We did not go up or down, so that coordinate is 0. And last, 270 degrees, which would be our negative y-axis, all the way down here. So with 270 degrees, we would get a radian measure of 3 pi over 2. And as we look for the x and y coordinates, we did not move left or right, so our x coordinate is 0. We came down 1 radius, so going down would give us -1. And that is the complete unit circle. And maybe the most important thing you can do for your study of trigonometry in pre-calculus next year is to commit this to memory. So we're going to work on some ways to do that in our next lessons.